Hey guys, welcome back. We're going to start looking at cylindrical coordinates today. And so as you guys can see over here in this nice little drawing, we have the cylindrical coordinates of r and theta. These are the exact same things with polars, where r is going to be the distance away from your pole, and then theta is going to represent as we are moving along the angle that's created from our radius here. And then we have this new component here, which is z, and z is actually going to create our height of our point, which basically is going to get us into a three-dimensional space. And then if we can somewhat look at this, it's going to end up creating, as we move around the pole here, we actually create ourselves a cylinder. And so the first thing we're going to notice here is that we have the Cartesian x, y, and z, and we're going to convert those to cylindrical of r, theta, and now rz. I also want us to notice that the z's are the exact same thing here. So whatever coordinate we give you for z in Cartesian or cylindrical will always be this corresponding coordinate in each of them. So first thing we're going to do is we're going to look at the equations that you see here. And again, if you're familiar with polars, then these are not unfamiliar to you guys. X equals r cosine of theta and y equals r sine of theta. This is derived simply by SOHCAHTOA. X squared plus y squared equals r squared is derived from Pythagorean theorem. And then we know our ratio of tangent of theta is just our y coordinate over our x coordinate. We are restricting this, so the radius has to be positive or equal to 0. So when we're looking at our point, we cannot go in a negative direction, so radius will always be positive. And since we're rotating around the plane, we are going to go from theta being 0 all the way back to 2 pi, and that's very common with like a unit circle problem. So let's go ahead and look at our equations, and let's look at the point. Let's do this first example here. So the first coordinate says, given the following coordinates, convert from Cartesian to cylindrical. So I want us to notice that right now, we're given us Cartesian coordinates in x, y, and z. So first thing we're going to do is let's find the r. Well, we're going to use the equation that you see right here. We're going to say that r squared is equal to x squared plus y squared. And so we actually know that x is going to be 3. So we're going to do 3 squared is 9. Y is also 3, so also 9. And so we get that r squared is equal to 18. And so we're going to go ahead and take the square root of 18. And we're going to just do a little quick simplification for this. And we're going to get that the square root of 18 ends up being positive 3 square root of 2. So the r coordinate in our first point here is going to be 3 square root of 2. And then we're going to go ahead and look at the theta, and we're going to use this equation right here. So tangent of theta is equal to y over x. And so just again, replacing our y with 3 and our x with 3 as well, we get that the tangent of theta is equal to 1. We also remember that we are in quadrant number 1 here, so positive, positive, positive. So we just know that we want where tangent is positive 1 in quadrant number 1. And so that's going to be where theta is equal to pi over 4. And so that is going to give us the theta coordinate for this particular example. And then just as I've mentioned before, the z coordinate is 5 for cylindrical and Cartesian. So we're going to have the same coordinate for that right there. So here's our first problem where 335 is converted to 3 square roots of 2, pi over 4, and then 5. All right, so let's go ahead and do one more example here, example number 2. And here we go with the problem. We're going to give us in x, y, and z. So first thing, our r squared is going to be equal to our x coordinate squared plus our y coordinate squared, right? So these are pretty straightforward examples, I hope. You know, especially if you guys have done polar coordinates before, which you should have, this would be second nature to you guys. So anyways, we get that this is 2 squared plus 0 squared, that is a 0. So I get r squared equals 4. So our r coordinate in this particular point is simply going to be 2. And then we're going to go over here and find our theta. So again, tangent of theta is going to be equal to our y coordinate, which is going to be 0, over our x coordinate, which is going to be 2. And so we're going to take the arctangent of 0, right, and figure out, okay, well, where's tangent 0? And so that's going to be at 0. And so we're going to go ahead and put 0 here for this. And just like I've mentioned before, that the coordinate that is z is -1, that is also going to be -1. So here are 2 pretty quick examples of this concept. You guys can try example number 3. You can pause the video for it, and then you can see if you get the right answer. So as you guys can see right here, hopefully you paused it, looked at it, and so the radius will end up being 4. Theta is actually undefined because it's 4 over 0. So where tangent is undefined is going to be pi over 2, and then z is equal to z. So these are the two equations that we used right here when we're going from Cartesian to cylindrical. So now we're going to go and do the other way. We're going to go cylindrical to Cartesian, and we're going to use these two equations that you see right here. So we're going to come down here, and we have two quick examples about this. And so we're going to go ahead and start and say that in this case here, remember that we're given cylindrical, and we're going to Cartesian with this. So this is going to be r, this is going to be theta, and then this is going to be our z coordinate. And so the first thing we're going to do is we've got to figure out what x is. Well, x is going to be equal to our r cosine of theta. And again, this is derived from SOHCAHTOA. Cosine of theta is just the adjacent side over the hypotenuse. And so we're going to go ahead and say that x is equal to our r, which is 4. And we're going to do the cosine of 2 pi over 3. And so cosine of 2 pi over 3 is going to be negative 1/2 because this is in quadrant 2. So we're going to get 4 times negative 1/2. And we're going to get that this x coordinate is going to be negative 2. And we're going to continue on with this one. We're going to do now y equals the exact same thing. The only difference is now instead of using cosine, we'll use sine. And so we're going to just go ahead and plug in as we see here. We get the 4 for our radius. We're going to take the sine of 2 pi over 3. Sine is positive in quadrant number 2, and it's the square root of 3 over 2. So we get 4 times the square root of 3 over 2. And then we get the positive answer of 2 square roots of 3 as our answer for this. And then just as I've said many times before, the z term is just going to be equal to the z term. So negative 3 is going to be equal to negative 3. And so when we summarize all this together, we're going to say that the coordinate that you're going to use here is going to be negative 2, again derived from r cosine of theta, and then 2 square roots of 3, and then finally negative 3. And so there we go. Pretty straightforward for this problem. So again, I'm going to ask you guys if you want to pause it and see if you can try this problem right here, and then we'll come back and make sure you get the right answer. So as you guys can see here, hopefully you got the right answer for this. So finding x, we do 5 cosine of theta, or r cosine theta. R is 5, cosine of theta is pi over 6. So we get 5 times cosine of pi over 6, which is square root of 3 over 2. So our first answer we get here is 5 square root of 3 over 2. We do the same thing with y, except for again we use sine. So sine of pi over 6 is positive 1/2. 5 times 5, we get 5/2, or 2.5. And again, the z coordinate will always be the z coordinate, so we get the 7. So here's our final answer for this problem. 5 square root of 3 over 2, 5 over 2, and then 7. I hope this is helpful, and we're going to continue our next video when we start looking at graphs and equations of these problems. So until next time, take care.